Welcome back on Electrical Machine 3. So as you can see, we have split our work to small work so that we emphasize our understanding for each point. So today we're going to talk about the voltage regulation, and then on the next video we're going to talk about the efficiency, and then the last one we're going to talk about the per unity. So which means once you understand how to deal with your voltage regulation in normal calculation, you understand how to do your calculation with the efficiency, the per unit will be simple, just an application of formulas. Okay, so give us time. The test will be on the 12th, if I think. So we still have time. By the end of the weekend, we're gonna do our efficiency. From next week, we just introduce the per unit, and then you'll see that you're gonna master this chapter. So as I said, we're going to talk about the voltage regulation, and then we're going to talk about the per unit voltage regulation, which we're going to be using more often when you start doing your calculation of a single phase transformer. But the question is, what is a voltage regulation? And therefore, when the when the secondary of the transformer is loaded, so if you have a load on the secondary voltage V2, which is a voltage drop due to the series impedance. Okay, so remember from the previous calculation where we were doing our calculation for the transformer, we have a ideal, we didn't have a load. Now we have a load. Can you see that? So therefore the induced EMF that we are inducing here is E2. That is the induced EMF. But because of this series impedance, which is this impedance here, we're gonna have a voltage drop. Therefore, the V out here, the V2 here is gonna be different. Can you see? So as you can see, if you apply your Kirchhoff, we know that the induced EMF will be equal to V2, okay, plus what? The voltage drop across that impedance. Can you see that? In that circuit, the voltage from the supply is always equal to the voltage, the addition of the voltage drop, and therefore our V2 is always going to be given by the V terminal, that's the V2. It's going to be equal to the induced EMF, which is our E2, minus the voltage drop. Can you see that? So that's what happens when you have a load. Because of those coil losses, we're going to have a voltage drop. Therefore, if I induce, for instance, 110 here, I may not get 110, I may get 105 because of those series impedance. Okay, so as you can see, sometimes this is also depends with the power factor angle. As the power factor decrease, this voltage drop increase. This is called the regulation of the transformer. It's usually expressed as per percentage. Okay, so you can see it's all about the one that I'm inducing minus the V terminal divided by the induced voltage times 100. Just to know what is the losses in our transformer, the voltage regulation. That's how you calculate it, and it's simple and straightforward. Okay, so we're gonna have a look on normally how you calculate and when you have to calculate it by unity. Okay, and then you can see that is a short chapter once you split them in small work. Okay, so now because we're gonna have a look on some problem solving under this voltage regulation, and then problem 1, we can see that they give us a given power, which is the rating of the transformer, 5 kVA, and then we have our KT ratio, which is gonna be 240. I think it was yeah. So this is gonna be our E1, the induced EMF 1. It's gonna be E1, and then you know that our E1 is gonna be equal to V1. Okay, and then the given this one 400 will be equal to our E2, the induced EMF 2, E2, and then it's gonna be different from our V2 because we have losses, we have an impedance, and then they give us the V terminal, and the V terminal we say is gonna be our what? V2, and then the question they say we must calculate our V terminal, the voltage regulation. So you apply this formula and then you get your voltage regulation. Simple and straightforward. On problem 2, they say open circuit voltage of a transformer, which means open circuit we have this to become our E2 when it was open. And then it states when the percentage voltage drop, which means they give us the voltage drop, our VR, voltage regulation. And they say we must calculate what will be the V terminal. And then you do some application here, you get your V terminal, which is the V2. Okay? So once you understand this, now let's have a look on this per unity impedance voltage regulation. So when it comes to the per unit voltage regulation, there's not much. It's just an application of a formula. Okay? So it's gonna be E2, I2, the voltage on the secondary, times the equivalent circuit. ZE2 refer to the secondary, and as well this is gonna be the angle of the impedance. Okay? Z equivalent, the angle of it, and as well the current angle of the current, I2. So we're gonna have, it depend, as I say, it depends with what will be our power factor. I believe this was a mistake. This is supposed to be leading power factor. Leading power factor. When you have leading power factor, you're gonna have an addition here. Lagging, you're going to subtract. Okay? So we're gonna have a look. What is the difference between this formula and the one that I gave previously, to see how we can make a difference between the two? But there is no much difference. But more often when you'll be doing your problem for machine 3, you'll be using this formula to calculate the voltage regulation. That one is just an introduction. Okay, so we're gonna prove it, but we can prove that the two is gonna lead us to the same solution. So we're gonna have a look on an example. So we're gonna have a look on an example, and then remember we have discussed already about this problem of doing the reference of the equivalent impedance to the primary, the secondary. We have discussed about it already. Okay, but we're just gonna do a recall again to explain what happened. I said previously that if we have to take this impedance Z1, it's always the bigger impedance. If we have to refer it to this, to the secondary, okay, we always divide it by the KT squared, KT ratio. So this guy referred to the secondary, it's gonna be the impedance Z1, okay, divide by the KT ratio squared. This will give us Z1 refer to the secondary, that the prime. Okay, but if we have to do the same again, we want to refer the Z equivalent to the primary. What happened? We want to take the Z2, okay, we times it by the KT ratio squared always, and then this is going to give us our impedance to refer to the primary, so that the addition of this plus Z1 will give us the Z equivalent 1. Okay, this is just a recall. But now look what happened here. In order for me to calculate my voltage regulation on the secondary, as we said, there will be a voltage drop. Our V terminal is going to be this minus that, so that we can get this voltage drop here. But remember, we said that those impedance Z1 and Z2, they are always referred to one side. But in the case when we are doing calculation of voltage regulation, we need to refer them to the secondary. And as I said, we're going to take the impedance Z1, we refer it to the secondary, then plus Z2, then we are going to get our ZE2. Okay? And to get that Z1, refer to the secondary, I explained, you take Z1, you divide by the KT squared. So, after understanding this, what happened now, we take the circuits, we apply our Kirchhoff rules, and I have explained already. We say the voltage rise must be equal to the voltage drop. Okay, remember in this case we come with a supply, we supply to the primary, where we say V1 must be equal to E1, so that we're gonna induce a EMF here, induce a flux here. This is of the mutual induction, there will be a flux that will be induced here, which means this on this case is the rise voltage. Can you see? So we have a rise voltage, which is the induced E2. So we say the current into a component is what? Positive, out of the component, negative. In the component, positive, out of the component, negative. So you can see this positive to a negative sign, we are dropping. So it's going to be VZE2. Positive to negative sign, we are dropping. So it's going to be V2. Okay? But our V2, the V terminal V2 is going to be the induced EMF E2 minus the voltage drop there. Okay? So that's basically what's going to happen. But in order for me to calculate this voltage, VZE2 is going to be I2 times ZE2. In order for us to calculate I2 is going to be the rating, the power of the transformer divided by V2. Simple and straightforward. So let's go down. This was just a small recall revision. So under question 5 of your tutorial 2020 that was given to you, they give us the impedance. They give us the resistor R1 and X1, which means we can calculate our impedance Z1 because of it's a resistor in combination. It's a RL circuit. So from electrical 2, this is how we calculate the total impedance of the two. Then you get your Z1, and then we say Z1 refer to the secondary, we divide it by KT squared, then for you gonna get your Z1 refer to the secondary. But the ZE2 is gonna be Z1 refer to the secondary plus Z2, and then you get your ZE2. And then as well you calculate your current I2. Okay, and then you take the given power factor in the problem. Remember the power factor, you calculate the angle. Okay, and therefore this current, remember we got it without an angle. From electrical 2, we say each component must always have what? A magnitude and the angle. So therefore, because it says lagging, this current is going to be 25 at minus. Minus, it means it's lagging. Okay? So after doing this, now you can calculate the V terminal 2. From the equation, we say V terminal 2 is going to be E2 I2 times ZE2. So the induced EMF is going to be always at the angle of 0. And then the given current is this. The ZE2 we have calculated is that. Then we can get our VE2. Okay? But remember, for the voltage regulation, for the first equation that I give, we said it's going to be the induced EMF minus VE2. So it's going to be like that. But remember, here you have angle and magnitude in complex mode. So finally, you're going to get this as the answer. Okay? But if you change it to rectangular form, this part here will be your voltage regulation. Okay, this is your voltage regulation. You ignore the imaginary part, but this is not applicable in machine 3. Now you're gonna need to apply the one for the per unity voltage regulation I give to you, and it's simple and straightforward to apply. It's just an application of formula. Okay, so when you go down, now we're gonna prove that the answer we got here, 5,587, is the same we're gonna get if you apply this equation. And then if this equation is changed, it's lagging. When it's lagging, you have negative. When it's leading, you have a positive. Okay, so you know that already. Okay, so our I2 we got, it was 25. Our ZE2, the magnitude is 1,02. The angle of that ZE2, the one we got, it was 65,7 degrees. The power factor angle that was given to us was 36,87, the angle. And our V2 is that. So if you apply this formula, you can see that the answer you got is the same as the one that we did from the previous calculation. But I will suggest you to use this formula always when you have to calculate the voltage regulation. So that it's straightforward. That's all about the voltage regulation. Any question, challenge, please always ask it in the group.